What is going on, everyone? Welcome back to another video. Today we are going to be doing a Fluent tutorial, the flow around an airfoil. Let's get into it. So in this tutorial, we are going to be doing a CFD simulation in Fluent ANSYS in order to simulate the flow around an airfoil. And for my example airfoil, I'm going to use the NACA 4415, but you can use any airfoil you'd like. In this tutorial, you'll learn how to plot an airfoil in SpaceClaim, and we'll use airfoil plotter tools to help us get the exact shape of the airfoil that we want. We're also going to learn how to build a C-type domain around the airfoil and how to mesh this C-type domain. We're also going to learn how to validate the mesh size using the Y+ metric. And again, we're going to use some calculators in order to estimate what it will be. You'll also learn how to initialize the simulation models, how to implement boundary conditions, and for result validation, you'll learn how to plot the lift and drag plots, as well as how to plot the velocity and pressure contours. And to the right of the slide, this is the expected results that we'll get for the simulation that we're doing for the NACA 4415. Granted, if you do another airfoil, you'll get slightly different results, but the process will be exactly the same. So let's get into it. So first things first, we got to do a bit of literature review and understand the key parameters that are at play. So as I mentioned, I'm going to be using the NACA 4415 as my example airfoil that has a chord length of 1 meter. And to the right-hand side here, I have some experimental data from Abbott and Company posted in 1945. And this shows the section lift, section drag, and moment coefficients as a function of the angle of attack of the airfoil. And this will help validate the results that we get because in ANSYS, we're going to be able to calculate the coefficient of lift and the coefficient of drag for our airfoil. And so we'll be able to compare it to a specific case from one of these graphs and be able to calculate the overall error that we've attained from running the simulation. So the particular case that we're going to do today for the NACA 4415 is we're going to have the flow around the airfoil of air, which is very standard. In ANSYS, it has the following parameters: a density of 1.225 kilograms per meter cubed and a viscosity of 1.7894, each in the -5 kilograms per meter second. And choosing a Reynolds number of 6 times 10 to the 6 and plugging it back into the Reynolds number formula and moving some parameters around, we can get our free stream velocity to be equal to 87.64 meters per second. Also, by choosing this Reynolds number of 6 times 10 to the 6, as we see in the legend in this graph here, the curve that represents this Reynolds number is the square data points. And so if we find the square data points here and say we choose an angle of attack of 0, well, we could get an expected coefficient of lift of 0.45 and a expected coefficient of drag of 0.0065. And so these are the results that we are expected to obtain from running the simulation in Fluent. So that being said, now that we know what the key parameters are and what the expected results are going to be, let's go ahead and start working on this simulation. So the first thing that we're going to do is go back a slide and open up this first link here to access the airfoil plotter tools that are available to us. And so this is the Airfoil plotter tool that is available online for free. There is a whole bunch of them, but I've chosen this one for our simulation today. And what this is going to allow us to do is obtain a file that has all of the graphical data points, or as many data points as you want, of the outer surface of the airfoil. And this will help us plot the exact shape in SpaceClaim later on. So a couple things to change here. First is the actual airfoil type. We're going to go ahead and choose our NACA 4415. But again, you could do this for any airfoil your heart desires. There it is. And as I mentioned in the slide beforehand, we're going to use a chord length of 1 meter or 1,000 millimeters. And the rest will leave the same. So go ahead and press on plot, which will reload the website. And as you can see now in the graph up here, now represents our NACA 4415 airfoil with a chord length of 1 meter. And we can go ahead and download the coordinate file by pressing CSV file of coordinates. And this is just going to create an Excel file. So if we go ahead and open this, we can now see all of our data of our airfoil, the coordinate points of our airfoil surface, and there's also more information for the camber line and chord line. However, this file is not readable by ANSYS, so we do need to modify it a little bit so that SpaceClaim can read it and create a line of our exact airfoil shape. So let's go ahead and make those modifications. The first thing that we're going to do is delete all this top information here right up until your first data point. So go ahead and delete that. And we're also going to get rid of all the other information for camber line and chord line. So you just want the coordinate points of your airfoil surface. Next, we're going to go ahead and grab all this data and cut it and move it to column B2. You do want to leave column A empty because we do need to add some information there. The information that we're going to add is a 1, and if you double click on the square at the bottom of the cell, this will just put a 1 in all of the rows where there is data. And what this parameter is going to do for us is indicate to SpaceClaim that we want to group all of these points into one singular line. And in order to actually plot the line, we need to have a command. And so in the first row here, we're going to insert our command, which is polyline with a capital P equals true. And this will create the polyline, grouping all of these coordinate points into one single line. And so that is all the modifications that we have to do to our Excel file for importing it into SpaceClaim. The next thing that we have to do is export it as a text file because Excel files are not actually readable by SpaceClaim. So let's do this. Go ahead and press on File and Save As, Browse. And I'm going to rename this to the NACA 4415. And the type is going to be a text file. And I'm just going to save it to my downloads. That's fine. Great. So now that we have a file that's going to be readable by SpaceClaim to create our airfoil shape, let's go ahead to jump into Workbench and open SpaceClaim so we can continue building the rest of the geometry for our simulation. Hey guys, now with SpaceClaim open, let's go ahead and open SpaceClaim to continue building our geometry. So in the middle here, this is our project schematic. This is where we're going to be building our whole simulation. And in the left-hand column here, these are our analysis systems that we use to build any simulation that we desire. But for this simulation, we're going to go ahead and grab the Fluid Flow Fluent analysis system and drag that into our project schematic. And we'll double click on geometry to launch SpaceClaim. So in the bottom left-hand corner here, it says starting SpaceClaim. So I'll wait for that to load. With SpaceClaim open, let's continue building our geometry. So by default, SpaceClaim has us sketching on the ZX plane, as you can see. It's preferable to sketch on the YX plane because it just makes it easier for initialization later on. So we'll go ahead and press on End Sketch Editing to choose a different plane. And so we'll re-enter sketch mode by pressing on the pencil crayon up here, and then we'll choose our plane. So we want to choose the XY plane. We'll press on the Z axis here on the coordinate system to make the screen normal for easier viewing. And now we're going to import the text file that we've created. But first thing that you need to do before you import the text file is you actually need to close the Excel file. And I learned this the hard way. For some reason, SpaceClaim won't let you import the text file if you still have the Excel file that it originated from open. So we need to make sure that this is closed. So I'll go to my hotbar and just close the Excel file. And now we'll be able to load the text file in SpaceClaim. So to load a text file, go ahead and press on the Assembly tab here and press on File. And this is going to prompt you to browse for a file. And in file type, we'll change this to text file or all files. And we see our text file, the NACA 4415 right here. So we'll click that and open it. And as you can see from the polyline command and the grouping of all of the coordinate points of our airfoil surface, SpaceClaim has gone ahead and created the exact airfoil shape of the NACA 4415. So that is great. So as you'll note from the design tree here as well, the text file imported as a curve because that's what we wanted. That was the command that we used. But for the rest of this, we're going to need a surface out of this airfoil shape. So we need to fill the surface that's within this curve that has been created. So to do this, I'm going to go ahead and press on the design tab up here. I'm going to select my airfoil. or the curve of my airfoil, and I'm going to use the fill command. And as you can see, now all the curves have converted into one singular surface. And you guys are probably wondering right now, well, why did I create a surface for my airfoil? This is a CFD simulation, and when we run some CFD simulations, we don't want the surface of our object, we want the surface around it to simulate the airflow that is around our object. And this is true. So we're going to continue building the surface around our airfoil, and then we'll subtract the airfoil surface from it to get the surface around the airfoil without the airfoil being included. And for the simulation, I'm going to go ahead and build a C-type domain. This is a domain that has a curved section in the front and a flat section behind the airfoil. There are a whole bunch of different domains that you could use for this simulation, but this type of domain has proven to be better for convergence. So let's go ahead and use that one. To start building it, I'm going to re-enter sketch mode by pressing on the pencil crayon and choosing the airfoil here. And the first thing that I'm going to do is grab the line command, and from my origin or the leading edge of the airfoil, I'm going to go ahead and draw a small line that's about 100 millimeters from the leading edge of the airfoil. And I'm going to press escape, and I'm going to convert this line into a construction line by right-clicking and pressing on the little dotted line here. So now this line has been converted into a construction line to help us build the rest of the curves that we need for the surface without it interfering with the creation of the surface. So next up, I'm going to grab the line command again, and from the end of my construction line that I've just created, I'll drag a line vertically. And this is going to represent the radius or width of my C domain. And we're going to make this length 7,500 millimeters. And I'll press escape and grab the line command again and go to the bottom of the line and drag a line vertically downwards of the same length, 7,500 millimeters. And I'm choosing this dimension for the surrounding air around my airfoil to be about 15 times the chord length that we have, which is 1 meter or 1,000 millimeters. And this should give sufficient space to give an accurate reading of the airflow around the airfoil without any interference from other places. To continue building the domain, I'm going to go ahead and press on escape because we don't need the line command anymore. And I'll use the circle command. I'll go to the middle of my construction line and drag a circle out to the top of my vertical lines that I've created. And then I'll take the trim command by pressing on the middle icon here in the modify section of our toolbar. And I'm going to trim away the semicircle that is at the back of the airfoil. And so this just leaves us with an arc at the front or the leading edge of the airfoil, which is the C part of our C-type domain. And the rest of our domain is just going to be filled with a rectangular box behind it. So to do this, I'm going to grab the line command, and from the top of my curve, I'm going to drag a line that is horizontally outwards. And again, I'm going to make this 15 times the chord length, or 15,000 millimeters. And then I'll drag a line vertically downwards that is aligned with the bottom of our curve, and then drag the line back to the curve to create a full surface. Press on escape. And these are the curves that we need for our C-type domain. We actually don't need the lines in here either. So we could actually go ahead and convert these to construction lines as well, so they don't interfere with the creation of our surface from the other curves. So now we can go ahead and convert these curves to a surface. To do this, I'm just going to end sketch editing, and it will create a surface from the curves that we've created. Next up, I'm going to go ahead and delete the airfoil surface from the domain that we've created here. So to do this, I'm going to go ahead and press on the combine command in the intersect part section of the toolbar. So the first thing that we need to select is a target object. So what domain we're targeting to remove something from it. So this is the big domain, or our CFD domain that we just created. So let's go ahead and choose that. And then the second option, we want to ensure that we have the cutter tool selected, and we need to choose the surface that we want to cut away from the target object. And this is the airfoil surface. So let's go ahead and select the airfoil surface. And if we press escape, It is not evident right now, but the airfoil has been cut away from the outer shape that we have here. So now we can go ahead and actually delete the airfoil surfaces. There will be two of them because we had the airfoil shape that we created with the text file. And since we cut away the airfoil shape from the C-type domain, there are two airfoil surfaces that are stacked on top of one another. We don't need either of them. We don't need the object geometry in a CFD simulation. So we can go ahead and delete both those. So just select the airfoil and press delete. And that got rid of one of them. As you can see in the design tree, we used to have two surfaces. Now we only have one, which is representative of both the surfaces that we have here. And I can go ahead and select the airfoil again and delete that again. And now we can see that we have white space where the airfoil was, which represents the background of our SpaceClaim environment. So now we just have the surface around the airfoil, which represents the fluid domain for this CFD simulation. And before we move on to the meshing stage and the initialization of boundary conditions, there's a couple more things that we have to do to our surface in order to make the control over the mesh a little easier. And what we're going to do is split this domain into a whole bunch of smaller domains. So to do this, I'm going to go ahead and choose the split command in the intersect section of our toolbar. The first thing that we have to do is click on the surface that we want to split. We only have one surface for right now. So let's go ahead and choose that surface. And using the first cutter command that we have here, we'll go ahead and choose the trailing edge of our airfoil. So make sure you choose the trailing edge of our airfoil, not one of the other points along the airfoil surface. And we'll press on escape. And as you can see, what was one surface has now been separated into four little surfaces. However, we do need to split these front surfaces a little bit more, again, to make the meshing a little easier later on. So let's go ahead and pick the split command again. For my surface, I'm going to go ahead and choose the top left quadrant to begin with. And instead of using the first command, I'm going to actually use the second cutting command, which creates a perpendicular line from where we choose its point. And the point that I'm going to choose is the intersection between the curve and the straight line that goes towards the trailing edge of our domain. And as you can see, a line has appeared that is going to cut the surface perpendicularly downwards from that point. So go ahead and press on that point. As you can see, now we have two surfaces where there used to be one, and we'll do the same thing for the bottom left quadrant as well. So again, pick the surface you want to cut, and using the perpendicular cutting command, I'm going to go ahead and choose the intersection point between the curve and the straight line. And so now you can press escape, and now we have 6 little surfaces that make up our CFD domain. And this will allow us to more easily control the mesh and get a better quality of mesh, greatly increasing the computational efficiency of our simulation that we're creating. But that is going to be it for the SpaceClaim part of this video. So we can go ahead and close SpaceClaim by clicking on the big X. And we'll return back to Workbench. So now we see we have a check mark beside geometry, so that is good to go. Next up, as I've hinted at, is the meshing part of this simulation. So let's go ahead and press on mesh. And in the bottom left, it says starting meshing. So I'll wait for that to load. Now with the mesher open, we can go ahead and start building the mesh for the geometry that we've created. I'm going to go ahead and press on the Z axis here to make it normal to the screen for better viewing. And as I normally do in a lot of these videos is I normally generate the default mesh from ANSYS with no extra sizings or anything. But I do know that for this particular geometry, it's not going to go very well. It's going to create a very coarse mesh and it's not going to be good. So let's go ahead and add the sizings before we create the mesh, just to have a little extra control over it. So the first thing that I'm going to do is add some sizings to some of the lines that we have here. So to add a sizing, I can right click on mesh, go to insert and press on sizing. As we can see in the bottom left here, these are the details for the sizing, and we have 2 yellow fields. Yellow fields in ANSYS means that it is waiting for user input in order to properly handle the object or command that we're defining. So the first thing that we need to do is choose our geometry. So for our geometry for the sizing, I'm going to go ahead and press on the edge selector command from the toolbar. And holding control, I'm going to choose all of the vertical lines that we have in our domain, as well as this front horizontal line in the front of our domain here. So you should have selected 7 lines. And now we can add this to our geometry. So we'll press on no selection and press on the apply button that appears. So we can see that there has been 7 edges added to our sizing, which has now turned into an edge sizing. For the type of sizing that we're going to do, we're not going to define the element size. If you press on element size and press on the triangle that appears, we're going to define the number of divisions. And the number of divisions that we're going to do along these lines is 200. And in the advanced settings of our sizing, we're going to go ahead and to the bottom here where it says bias type, and we are going to introduce a bias to our sizing. So by pressing on no bias and pressing on the drop-down menu that appears, we'll select the first option that we have here. There's another field that appears here that says, please define the bias factor. And for this bias, I'm going to specify a factor of 40,000. There we have it. And so what does a bias do? Well, if we now look at the number of divisions along the lines that we've selected, we can see that the elements that are farther away from the airfoil for some of the lines are going to be bigger. And as it moves towards the airfoils, the divisions are getting smaller and smaller. So what the bias allows us to do is keep the same number of divisions, but make the elements smaller in more critical areas so that we can capture smaller details of the flow, such as over the airfoil. And in areas where it doesn't matter as much, we can have a larger size element. But overall, there's the same amount of elements that there would be had we just keep them of equal size. We do see that there are a couple lines here that show that there's going to be bigger elements towards the airfoil. That's not good. We do want the smaller elements to be closer to our airfoil because we want to capture the smaller details of flow that happen around the airfoil. So I'm going to go ahead and choose the edge selector command again. I'm going to choose the edges that I want to reverse by holding control. And where it says reverse bias, no selection, I'm going to press on no selection and press on the apply button that appears. So now that we can see that there's been 3 edges where we are going to reverse the bias that we had initially. So that's going to be good for these edges. So let's add a couple more sizings. I'm going to go right click on mesh, go to insert and press on sizing. That's a contact sizing. That's the wrong one. So if ever you implement the wrong function, you could always delete it. So right click on the function and press on delete. Do you want to delete this object? Yes. I wanted to insert a regular sizing, not a contact sizing. Again, the yellow fields means that we need to specify what we want to do with this sizing. So I'm going to go ahead and select some more edges. So using the edge selector command, I'm going to go ahead and choose these 3 edges here in the trailing edge of our domain. I'm going to press on apply. So now there's been 3 edges added to our sizing. And for element size, I'm going to change this to number of divisions, and I'm going to choose the number of divisions to be 300. And again, since we care more about the airflow near the airfoil, and we don't care so much what the flow is going to be like way downstream at the back of our domain, I'm going to go ahead and add a bias. So where it says no bias, I'm going to add the first option for the bias, which is going to congregate all of the divisions to be closer to the airfoil. And for the bias factor, I'm going to put 40,000. And we can see that 2 of our lines need to be reversed because we want the smaller elements to be closer to the airfoil. So I'll select those 2 lines by holding control, and I'll press on reverse bias, apply. So now that there's been 2 edges that will have the reverse bias and 1 edge that has the regular bias. We're going to go ahead and add another sizing now. So right click on mesh, go to insert and press on sizing. And now we are going to size the 4 little lines that we have here along the airfoil. So using the edge selector command and pressing on control, I'm going to select these 4 lines, press on apply. So now we have 4 edges that's been added to our 3rd sizing. And again, for the type, I'm going to specify the number of divisions. And since we care about this section of the airfoil, this is a very critical section for us, I'm going to put a lot of divisions along this very short distance. So I'm going to go ahead and add 300 for the number of divisions. And the reason why I had to separate this from edge sizing number 2 is because we don't actually want a bias for these surfaces, as they are the surfaces that are directly over our airfoil. So we want the elements to be of equal distance here, or of equal size. So that is it for our third sizing, and we'll go ahead and add another sizing for the remaining edges that are at the front of our domain. So let's go ahead and go to Insert and go to Sizing. And now I'm going to choose my 4 remaining edges. I'll go ahead and press on Apply. So now that there's been 4 edges added to the sizing. And for the type, I'm going to choose the number of divisions. And for the actual number of divisions, I'm going to choose 300. Again, I'm not going to have a bias since we are selecting the edges around our airfoil, so we want these elements to be of equal size. So that should be it for the sizings that we need to control our mesh. So now we can go ahead and generate the mesh, which will take into consideration all of these sizings. So let's go ahead and right-click on Mesh and press on Generate Mesh. So as we can see, the mesh has been created based on all of the edge sizings that we've created. And I actually forgot to add a function. So that is why the mesh doesn't look so great right now. We are going to add some face meshing in order to control the shape of the elements that is created within the mesh. So let's go ahead and do that. Let's go to Insert, go to Face Meshing here. And so now we need to choose the geometry that we are meshing. Using the face selector command, we're going to choose all of our faces. So we have 6 faces. And as we can see, we've only selected 5. So let's go ahead and reselect all these faces again. So now we have 6 faces that have been added to our face meshing. And for the method type, we want to choose this as quadrilaterals because we want the elements to be very orthogonal within our mesh. So this should control the mesh and make the elements very orthogonal and prevent any skewing of our elements within the mesh that it creates. So let's go ahead and regenerate the mesh. Right click on Mesh, press on Generate Mesh. And as you can see, based on our edge sizings and now our face meshing that I forgot to add before, our mesh is a lot more orthogonal. All the elements are very square because we confined with our face meshing the elements to be quadrilaterals instead of all of these skewed elements that we had before. And we can see that this is a very good domain as well. We can see that in the tops of our domain, the elements are a lot bigger. We don't care so much about the detail of the flow there, but right around our airfoil and in the trailing edge or trailing flow from our airfoil, the elements are much, much smaller. So that should be good to go. However, there is a metric that we can use, as I mentioned, the Y plus metric, which will help validate the size of our elements right around our airfoil to ensure that they're small enough in order to capture the boundary effect of the wall of the airfoil. So let's go ahead and move back to the PowerPoint to learn a little bit about what the Y plus metric is. So what is the Y plus metric or the wall distance Y plus? Well, it's a non-dimensional distance from the wall that is used to resolve nonlinearities in the flow at the boundary layer of our domain. This will essentially allow us to resolve the small turbulence flow that we expect to have over the airfoil right at the boundary layer, and this will essentially help us ensure a more accurate solution for our simulation. Based on the formulas that we can see here, we can see that the Y plus metric is a function of a couple things. Y, the physical distance, nu, the kinematic viscosity, and U, which is the friction velocity, which this itself is equal to the square root of the wall shear stress divided by the density of our fluid. And so what are some typical values for the y plus metric? Well, the y plus metric that is below 5 is what we're most interested in, as this will allow us to resolve the viscous sublayer. So what does this mean? Well, we can see that this is our nonlinearity that we have in our flow, and below this first green line here is our viscous sublayer. So if our first cell height was below the y plus of 5, we would be able to capture this nonlinear behavior of the flow within that area. If we have a y plus of 30, between 30 and 300, for example, well, then we are grouping all of this viscous sublayer, buffer layer, and inner layer that we have here, averaging the nonlinearity over a bigger distance. This would still help us capture some of the turbulent flow that we expect to see, but definitely it is not nearly as good as capturing the very specific and small nonlinear behavior that we see within the viscous sublayer. And if we were to have a y plus value that was greater than 300, well, this is completely undesirable since we are no longer able to accurately capture the turbulence of the flow near the wall, since now the elements are too large and is averaging the flow around the airfoil over too great of a distance, essentially nullifying these small non-linearities and details within the flow that we do want to see, because the boundary layer does affect the flow right around the airfoil. And it should be noted that based on the y plus value and the formula that we have here, that we can see that it's based on the friction velocity, which is actually an output to our simulation. And we are going to plot the y plus value after we perform this simulation to ensure that our solution is accurate and that we're actually capturing these non-linearities within this viscous sublayer. And this would allow us to actually create a mesh study to ensure that the mesh that we have created is small enough to give an accurate solution without compromising too much the computational efficiency. Because if you make the mesh really, really small and run the simulation with a lot of elements, well, this is kind of unnecessary, because below a y plus value of 5, the solution that we are going to get is not really going to change, because this is as small as a value that we need for our first cell height. So if we made them any smaller, we're just wasting computational efficiency to get the same accuracy of solution. However, if we were to have bigger elements, say within this bridging of our different layers here, well, now we are compromising and getting a less accurate simulation, but using less elements because they're bigger and saving on computational power. So by plotting the y plus metric at the end of the solution or the simulation would allow you to create a mesh study. So you would go back, fix your mesh, and then come back, rerun the simulation, and you can see how the solution would get more accurate over time by making the elements in the mesh smaller up until a certain point. And so how do we ensure that the y plus metric is going to be okay? Is there a way to estimate it? Well, yes, there is. There's some tools that we can use based on the characteristics of the flow, free stream velocity, the density, and the viscosity to help us estimate what the y plus value is. And this will help us, as I mentioned, validate the mesh that we've created before we move on to the initialization of boundary conditions, to not skip the mesh study, but help us start with a good value for what our first cell height should be right off of our airfoil, again, to capture these non-linearities in the flow. So let's go ahead and press on the link that we have here in order to access a tool that will help us estimate what the y plus value will be. So this is a y plus distance estimation calculator provided by CFD Online, another free resource for you guys to use. And as you can see, it requires a few inputs. One of them is the free stream velocity. And based on the input data that we provided from the slides and the Reynolds number, we determine this free stream velocity to be 87.64 meters per second. The density of our fluid, as initialized by ANSYS, is actually 1.225 kilograms per meter cubed. The dynamic viscosity, again, as I mentioned in the PowerPoint in ANSYS, has a magnitude of 1.7894 e to the minus 5. And our boundary layer length, this is simply our reference length or our chord length, which is equal to 1 meter, so that is good, and the desired y plus value that we want to get. As I mentioned, in order to capture the viscous sublayer, our y plus value needs to be below a value of 5. So for our desired value, I'm just going to put 3, which will allow all the elements of the mesh to be a little bit bigger, saving a little bit on computational power, but we are still well below the cutoff range of our viscous sublayer. So now I can go ahead and press on estimate wall distance. And as you can see, the output from this calculation gives us the Reynolds number of 6.0 times 10 to the 6 that we specified in our problem statement. And it gives us an estimated wall distance of 1.3 e to the minus 5 meters. So this means that our first element height right off of our airfoil needs to be smaller than this distance. So let's go ahead and jump back into the mesher to ensure that our y plus metric is being respected. So now that we're back in the mesher, let's go ahead and estimate what the distance is for our first cell height off of our airfoil. So let's zoom in all the way into our airfoil and choose one of these elements here. We'll need to go a little bit. So now we can see the first element height of our first element off of our airfoil. And to measure this distance that we have here, we'll use the first command here, which is the node command. So we can actually choose certain nodes within our mesh. And we'll go ahead and press on the first node along our airfoil. And holding control, we'll take the next node that is on top of it. And in the bottom right-hand corner here, we see that we have 2 nodes selected, and this gives us a distance of 9.6 times 10 to the negative 6 meters, which is below what the estimated y plus metric was that we calculated using the online tools based on the properties of our fluid. So that being said, the elements that we've created here should accurately capture the nonlinearities of the flow that will be right at our boundary layer. So what if our first cell height was not actually below the y plus value that we wanted? Well, there's a couple of things that we can do. The first thing that you can do is increase the number of divisions in order to get more divisions along that length, essentially decreasing the size of each element. So that could work. But the drawback to this is that you're going to add a lot of computational power necessary because you're adding a lot of elements. The best way to get your first cell height below that certain value is with the bias factor. So by increasing the bias factor, what you would do is congregate more of the elements towards the airfoil, making the elements near the airfoil smaller. So by increasing the bias factor, you would get smaller, even smaller elements towards your airfoil. And you would still have the same computational power because you're still using the same number of elements that you had before. So this is how you would modify your mesh in order to get a y plus metric that you desire. So now that we ensured that the quality of this mesh will be good for our simulation, there's one more thing that we need to do before we actually move on to the setup in Fluent, and this is adding some name selections, which is going to make the initialization of the boundary conditions a little bit easier. So for the name selections, we're just going to name some areas on our mesh that describe what type of boundary condition it is. So the first thing that we're going to name is the outlet. And so to do this, I'm going to go ahead and choose the edge selector tool. And I'm going to choose, by holding control, all of these edges along the outside of my mesh, excluding the ones that are directly at the back, because these will describe our outlet. So just choose the ones around our C-type domain and right-click and press on name selection. And we're going to name this the inlet. Using the edge selector tool, we'll go ahead and choose the 2 edges at the back and right-click, create name selection, and we'll name this the outlet. Press on OK. So now we can see that there has been a part added to our design tree here called name selections, which are the name selections that we just created. And again, this will help for initialization of boundary conditions later on. And we will also add one for the wall of our airfoil. So again, using the edge selector command, we'll go ahead and choose the edges of the airfoil. Not that edge, get a little closer. So these are all the edges. Right click, go to create name selection, and we'll call this wall. And we'll also create one for the actual fluid flow. So I'm going to use the face selector command instead, and I'm going to choose all of my faces by holding Control. I'm going to go to right click, create name selection, and I'm going to name this fluid domain. So now we've created a whole bunch of name selections for our mesh that we created. So that should be it for the meshing stage of this simulation. We can go ahead and now close the mesher by clicking on the big X at the top, and we can return back to Workbench. As you can see, we have a lightning bolt upon leaving the meshing stage. So why did this happen? When we generate the mesh, normally all this data gets translated to the setup of the program, but when we add name selections, they normally don't, and we do need to update this module so that all these information that we created during the meshing stage gets sent to the setup of the simulation in Fluent. So to update this, we'll just right click, press on update. So now you can see that we have a check mark beside mesh, so that is all good to go. Next is the setup of the program, so we can go ahead and double click on setup. In the bottom left corner, it says starting Fluent, and we're met with the Fluent launcher here. We're doing a 2D simulation, so that is good. We'll use double precision for this simulation. It's a fairly computational efficient simulation and doesn't require a lot of resources, so we can go for more precision. And for the solver processes, I'm going to put this to 2, and in parallel settings, I'll put the GPUs per machine to 1. And this is dependent on what machine you're running ANSYS on, but these are pretty generic numbers for any computer. And this will just help ANSYS delegate more resources to the solving of your simulation, essentially making the simulation run a little faster. So with all this initialize in the Fluent launcher, we can go ahead and press on start to launch Fluent. So now it says starting Fluent, so I'll wait for Fluent to load. Now with Fluent open, we can go ahead and initialize the model, set up the boundary conditions, and actually run the simulation. But before we do any of that, we're going to go ahead and double check our mesh to make sure it is good to go for Fluent. So if we go ahead and press on the check button in the mesh section of the general information here, it will plot some information to the console window here. And what we're interested in is the volume statistics, the minimum, maximum, and total volume. And we just want to make sure that all of these values are positive values. It is possible that you end up getting a negative value after the meshing stage. However, this will cause errors during the calculations because it's physically impossible to have a negative value. So if you do see a negative value here, you'll have to go back and fix your mesh in the meshing stage before you continue on with the simulation so that you don't run into calculation errors. But this is good to go for now. For the solver, we're going to leave all this information the same. Pressure-based solver, time is going to be steady, and 2D planar space, so that's all good to go. Let's double check our models to make sure they're good. So double click on models. And here we're particularly interested in the viscous model, which is the SST-K omega. This is the model that we want to use for this airfoil simulation. So that is good to go. We don't need to change it. And we're going to leave all the other models as off. So that is fine. Next, we could check the material that we're using. So if we double click on materials, we can see that by default, ANSYS has air in a fluid material and aluminum in the solid material. We can ignore the solid material. If we double click on air, this will open up this window here, and here we can see the properties of air that is by default in ANSYS, and it's 1.225 and 1.7894 for the density and viscosity respectively. And this is the same values that are presented in the problem statement. If you were to run the simulation, say you need to run it at a different altitude where the properties of air are different, say you had a lower density and a lower viscosity or whatever you need, you could go ahead and change these values. Simply write your new value in this field here and press on change and create, and this will update the properties for the material of air in this instance of Fluent for this simulation. But for right now, I'm going to leave it as is, so I'll close this window. And next up is initializing the cell zone conditions. So if I click on cell zone conditions, double click, we could see the fluid domain, which is one of the name selections that we created during the meshing stage. If we press on it, we can see that the type is fluid, so that is good. And if we press on edit, we can see that the material name by default is initialized as air, so that's all good to go. If you had other materials that you wanted to initialize for your fluid domain or your CFD domain, you would have to add it to the material trees here, and then you would initialize your CFD with the material of your choice by pressing on the drop-down menu, and all of your other materials would be listed here. But again, this is an airfoil simulation, so we're going to be simulating it in air, so that is good to go. We'll close this window. And next up, we'll move on to the boundary conditions. So if we double click on boundary conditions, again, we can see some of the name selections that we created during the meshing stage. If we press on the inlet, we check the type is a velocity inlet. So that is good because we want to specify what the free stream velocity is that is going to be coming in through the inlet of our CFD domain to reach our airfoil. If we press on edit, this is where we can initialize what the magnitude of our velocity is going to be. I'm going to, for the velocity specification method, I'm going to use components because this just makes it easier to control the direction that it is coming from. Since the angle of attack is 0 for this simulation, we know that we would only have flow in the x direction, which would be equal to 87.64, which we calculated during the PowerPoint presentation at the beginning of this video to give us a Reynolds number of 6.0 times 10 to the 6. If you did have a specific angle attack, say 1, 2, 3, 4 degrees, you would have to resolve the velocity into its respective x and y components to describe what the angle of attack to the airfoil would be. But for the simulation, we have a 0 angle of attack, so we're only going to have flow in the x direction. So that is good. I'll go ahead and press on apply, and I'll close this window. Next up is the outlet. We can see that it is a pressure outlet, so that is good. If we press on edit, we can see that the outlet is operating at gauge pressure of 0 pascals, meaning that our airfoil is operating at atmospheric pressure. And how do I know this? Well, if I close this window and I press on operating conditions, we can see that the operating pressure is 101,325 pascals, which is equal to 1 atmospheric pressure. And this operating pressure just means that this is the pressure that is everywhere in my environment. So that is good. And lastly, we're going to check the wall boundary condition. So if we press on wall, we can see that the type is wall. That is good. Press on edit. And in this window that appears here, we can see that the wall has a stationary motion. So that is good. We don't want it to be moving. And we want the no slip boundary condition checked off. So that is all good to go. Next, we're going to set up the reference values. So if we double click on reference values, we're going to compute the reference values from the inlet. And this just makes sure that we have all of the correct initialization here, mainly the velocity that we added for the inlet boundary condition. And that is it for the setup of our model. We can go ahead and move on to the solution part of the tree here to actually set up what kind of monitors we want and actually run the simulation. The first thing that we're going to check is the methods. So if we double click on methods, we can see that the scheme that we're using is a coupled scheme. You could change this to any of the other schemes that we have here. This is a fairly computationally easy simulation for ANSYS to solve. So any of these schemes would be very accurate, but I'm going to leave this as coupled for now. And on the subject of accuracy, we're going to go ahead and check our residuals by pressing on the plus beside monitors and double clicking on residuals. And we can see that the residuals for this simulation has an absolute criteria of convergence of 0.001. This is a fairly standard convergence criteria. However, as I mentioned before, this is a fairly simple and computationally easy simulation for the computer to solve. So we could afford to go for a little bit higher accuracy for our simulation because we have the available computational resources to do that. So for the absolute criteria for all my residuals, I'm going to go ahead and put 1e to the negative 6 and copy paste this for each of the residuals, like so. I'm going to go ahead and press on OK to confirm those changes. And now we're going to set up all the other monitors for all the variables that we want to see from the iterative calculation process. So if we right click on report definitions, go to new, go to force report and press on drag. This is going to create a drag report definition for the drag coefficient, which will allow us to monitor the drag coefficient calculation through each iteration of the calculation during the simulation. So I'm going to name this drag coefficient just to remember what this report was for. And the type is going to be drag coefficient, so that is good. We're going to want to calculate the drag coefficient over the wall of the airfoil. So make sure you select the wall. For the options here, we're going to calculate it over every iteration. That is fine. And for the force vector, we need to specify which direction this force is going to be in. From airfoil theory, we know that the drag over an airfoil is parallel to the free stream velocity. And since we had a zero angle of attack, we only had velocity in the x direction. So our drag would also be in the x direction, as noted by the 1 here, and the 0 in the y. If you did have an angle of attack, say of 1, 2, or 3 degrees, like you did for the velocity, you would have to revolve the components in the x and the y directions to get your force vector parallel to the free stream velocity. And I'll show you guys a slide a little bit later on once we've gone through one of these simulations to show how this can be done. But for a zero angle of attack, this is what our force vector would be. And lastly, we're going to print this to console. And this is just going to plot a graph of the iterative process of calculating the drag coefficient. So we'll go ahead and press on OK. And we're going to do the exact same thing, but for the coefficient of lift. So right click on report definitions, go to new, go to force, and go to lift. We're going to name this the coefficient of lift. And it's going to calculate the coefficient of lift over the wall of our airfoil. For every iteration, the force vector is going to be 1 in the y, which means it is perpendicular to the free stream velocity. And again, if you had a specific angle of attack that was different than 0, then you would have to resolve these components to get the correct force vector. And we are going to print this to the console again to see the graph over the iterative calculations. Press on OK. And now the monitors are set up for the variables that we want to see from this simulation. So we can go ahead and initialize the simulation by pressing on initialize or double clicking on initialization. And we're going to use the hybrid initialization. So press on initialize, and this is going to start writing the initialization to the console window here. And what hybrid initialization is doing for us is essentially setting up an initial value or a guess in each of the cells of our mesh. And this just serves as a starting point for running the calculations and starting off the iteration process that the simulation in Fluent is going to do. So now in the console window, we can see that it says hybrid initialization is done. So that is good to go. Next up is actually running the calculation. So let's go ahead and press on run calculation. And we're going to leave all of these fields the same, except for the number of iterations. We are going to run the simulation for 1,250 iterations. Go ahead and press on calculate. And as a result of pressing on calculate, it's going to start writing the iterative calculations in the console window here. And in the viewing window, we're going to see the scaled residuals, the graphs for the scaled residuals, and the graphs for the coefficient of lift and the coefficient of drag, since we printed it to the console window. And so we'll be able to see how the graphs are doing over time throughout the calculation process. So since this will take some time, with the magic of editing, I'm going to go ahead and cut to when it is finished, just so you guys don't have to sit through the whole time that it is running the calculation. So I'll see you guys in just a second. Hey guys, welcome back. The simulation is finished running, so we can go ahead and view the results that we've obtained. We'll go ahead and press on the OK button beside calculation complete. And the first thing that we're going to do is check the residuals and check the solution we got for the coefficient of drag and the coefficient of lift to be able to compare it to the experimental data that I presented in the slides. So let's do that. We're going to go ahead and press on the scaled residuals. And we can see that from running the simulation, the residuals dropped to a fairly low value. Though in the console window, we can see that the simulation did run through all 1,250 iterations. We do see that there are little to no changes in most of these residuals beyond the 200 iteration mark all the way to the end. So it can be concluded that the results converge to some value, just not to the degree of accuracy that we wanted. Had it reached the convergent criteria of 1e to the -6 for all of the residuals, then the iterative calculation would have terminated itself. So having run the calculation for maybe another 250 iterations would have probably converged to the criteria that we wanted. From the console window, we can also see what our coefficient of lift and what the calculated coefficient of drag is. The coefficient of lift can be seen to be 0.40125, and the coefficient of drag can be seen to be 0.0095435. And from the PowerPoint slide, from the experimental data presented by Abbott and Company, we saw that for a zero angle of attack with a Reynolds number of 6 times 10 to the 6, we would have gotten a coefficient of lift of 0.45 and a coefficient of drag of 0.0065, which if we calculate it gives us a percent error of about 10.8%, which is very good for the first time running this simulation, considering that we haven't not even performed a mesh study yet. If we are to plot the y plus metric and go back and fix up the size of our mesh elements, it's only expected that the error would drop even lower than this result. But anything below 15% for a first time calculation is a very good result. So now that we've validated the results that we've obtained, we can go ahead and visualize the results as well. To do this, we can plot some contours. So if we go to the graphics tab in the results section here, press on the plus beside graphics, we can see contours, right click on contours and press on new. For the first contour we're going to visualize is the pressure. So we're going to name this pressure contour. And the contour is going to be of pressure and the static pressure. And this is going to remain the same. Press on save and display. And in the console window here, we can see that the static pressure contour has been plotted for our simulation. I'm going to go ahead and close this. And if we zoom in, we can see that the result that we have obtained is fairly good. At the front of the airfoil, we can see that we have the highest pressure, which corresponds to the stagnation point at the leading edge of our airfoil. And we know from airfoils, lift from an airfoil works by creating an area of high pressure on the bottom of the airfoil and low pressure over the top of the airfoil. And this pressure gradient causes there to be lift. Therefore, the pressure contour that we have here is very consistent with the expected theory of an airfoil. We could also go ahead and plot the velocity to see what the velocity would be over the airfoil. To do this, let's go ahead and create a new contour. So right click on contour, go to new, and instead of pressure contour, first of all, I'm going to name this velocity. Contour. And for the contour of velocity, and we're going to plot the velocity magnitude, press on save and display. And we can see that this is our velocity contour for the simulation that we created here. And it gives a similar story to the pressure contour that we had. In the front here, we could see that the velocity goes to 0, corresponding to the very high pressure point that we had in the pressure contour, indicating our stagnation point at the leading edge of the airfoil. And we can see that over the top of the airfoil, the flow is moving a lot faster in the area of lower pressure, and the flow over the bottom of the airfoil is moving a little slower, allowing there to be higher pressure, which would again be the leading cause of the lift. We can also see that this airfoil with this angle of attack is fairly streamlined. We don't have much separation of the flow from the airfoil until we get to the very tip at the trailing edge of it. And we can see that we have a little streamline that continues on to the end of our CFD domain. So overall, this is a fairly good result and is consistent with the expected physics of an airfoil. The last thing that we can do is actually plot the y plus metric because, as I mentioned while we were validating the mesh, the y plus metric is actually an output to the simulation because it's dependent on the friction velocity. So we could go ahead and plot that by going to the plot section in the results here and pressing on the plus beside plots and plotting an XY plot. So right click on XY plot, press new. We're going to rename this to Y plus. And in the y-axis function here, we're going to choose turbulence because, again, as I mentioned, the y plus metric is to analyze the nonlinearities in flow or the turbulence. And in this drop-down menu, we can actually go find the wall y plus metric. And the surfaces on which we're going to plot this across is the wall or the surface of the airfoil. So press on save and plot, and this will plot the graph to the screen here. And as you can see, the y plus metric over the airfoil. So this is, as you can see, position is 0 to 1 as we initialize at the beginning, our chord length to be 1 meter. And we can see that as the flow goes over the airfoil, our wall y plus metric changes. And at the highest point, we can see that our y plus reached 2.03, which is well below the target value of 3 that we wanted in order to capture the details of the flow in the viscous sublayer. If you plot the y plus metric and you see that the value is going above your target value, or more importantly, above a y plus metric of 5, where we are no longer within the viscous sublayer region, then it's important that you go back to your mesh and update your mesh, make the first cell height over your airfoil a little bit smaller, preferably by changing or increasing your bias, and rerunning the simulation until you get a desired y plus value. And over time of you doing this, you should see that your percent error between your coefficient of lift and coefficient of drag to expected or theoretical results would diminish. But since the y plus value for my case is below even the target value of 3 that I wanted, I'll go ahead and conclude that this simulation was run with a fairly high degree of accuracy. Last thing before I let you guys go, I just want to go back to the slides and give you guys a little bit more information about the angle of attack and how this changes the components in X and Y for velocity, but more importantly, the components in X and Y for our force vectors. So let's go ahead and go back to the PowerPoint to view this last slide. Hey guys, last thing before I end the video, I just wanted to present to you guys one last slide in order to make your lives a little bit easier if you wanted to simulate a free stream velocity that had a non-zero angle of attack. As I mentioned while we were setting up these parameters, there are a few things that we would need to change if we were to simulate a non-zero angle of attack. First of all is our free stream velocity. Since we are not changing the pitch of the airfoil and we're simply changing the direction at which the velocity is hitting the airfoil, we need to resolve our components in X and Y and implement that into the boundary condition of our inlet. And so the formulas for this would be U, which is our free stream velocity, times cosine alpha, alpha in this case being our angle of attack. And for the Y component, the magnitude of velocity would be U sine of alpha. And as we know from aerodynamic theory, the drag force vector is going to be parallel to the free stream velocity, and the lift force vector is going to be perpendicular from the free stream velocity. So when we're defining report definitions in Fluent, we need to make sure that we are no longer putting 1 and 0 because this specifies a zero angle of attack. We need to actually revolve the angle of attack or the angle that we want into our components for our force vectors. So to do this for the lift force, for our X component, we would have a negative sine alpha, again, alpha being the angle of attack that we want. And for the Y component of the lift force, we would have cosine alpha. And for the drag force, it would be similar. In the X component, we would have cosine alpha, and in the Y component, we would have sine alpha. And so if we go back to Fluent, and go to report definitions and double click on one of the report definitions. This is where you would put your new information. And so for the components of the force vector, for the coefficient of lift, as I mentioned in the slides, in X would be negative sine alpha and in Y would be cosine alpha. And for the coefficient of drag, if we press on coefficient of drag, the force vector in X would be cosine alpha and the force vector in Y would be sine alpha to properly revolve the vectors with a non-zero angle of attack. So with this information, you guys should be able to try solving a simulation with a non-zero angle of attack on the airfoil of your choice. And so that being said, that will be it for this tutorial. Don't forget to like the video if you guys thought it was helpful and subscribe for more engineering content.